Alright, so today we're going to do our first lesson for chapter 5 on momentum. So this is on your sheet. It says lesson 6, momentum and impulse. Alright, so what is momentum? Let's go back and look at Newton's second law first. Newton's second law is written as the sum of all forces equals mass times acceleration. However, Newton actually didn't write it like this. Instead, let's take acceleration and write as, well, what's the definition of acceleration? And it's written as the change in velocity over time. And then we multiply both sides by time, and you get a force, a net force acting on an object over some time t, will change the object's velocity. Okay, now this is called an impulse. And this is called, a change in momentum, which I'll write as delta p. Now momentum is a vector, right? Just like impulse is a vector. And it's written as mass times velocity. You can think of it as the power behind a moving object. Right? So for example, which would have more momentum? A fly moving at 100 kilometers per hour, or a pickup truck moving at 100 kilometers per hour. Probably wouldn't be too worried about the fly. Right? However, if you had a bullet, that would be moving a lot faster, so that would be dangerous. It has a lot of momentum. Okay? Or, I don't know, some massive object moving very slowly. Like if the moon were to slowly be crashing into the earth, that would be dangerous too. No worries though, the moon is actually getting further from the earth. Right? The dinosaurs would have seen a much bigger moon. But I'm going off on a tangent now, so let's get back to momentum. So you can think of it as the power behind a moving object. It doesn't have any special units all to itself. Right? It just has units of mass times velocity, which would be kilograms meters per second. Those are the units of momentum. And of course it has a direction, and its direction is the same as the velocity of that object. Okay? So this equation works great, right? Newton says we have an impulse, and an impulse is just a force acting on some object over time to change its momentum. Right? So sometimes we write it as just impulse equals change in momentum. Okay, and there's a couple examples we can think of here. So let's think of sports. Sports is a good example. In almost every sport, we have follow-through, right? Like someone swinging a golf club, right? Doesn't stop when he reaches the ground, he follows through. Same with baseball, doesn't stop here, follows through. You always follow through. Tennis, follow through. Okay, why do you follow through? Well, in most of these sports, usually the goal is to get the greatest change in velocity. Right? Now you can't change the mass of the object, like the golf ball. You can't change the mass of the golf ball, right? But you want this to be as great as possible, usually. So you have two objects. What can you do with impulse? Two options. So you have two options. What can you do with impulse? You could increase the force and just start going to the gym. And professional players will do that. But another option is to increase the time you're in collision for. Right? And following through does do that. It doesn't seem like it because it happens in an instant, but if you had like a slow motion camera taking 70,000 frames per second, you can see that following through could double or triple your time in contact. And that means you double or triple your change in velocity. Right? You double your time, you double your change in velocity. That's a huge difference. Right? Changing something from 1 millisecond to 2 milliseconds doubles that change in velocity. So follow through is important. Another thing that's important is getting into a car accident. Getting into a car accident is not important. Don't do that. But this equation is important to help keep occupants of a car safe. How? Well, let's say you're in a car. Right? There's my car. And here's an impenetrable wall. And you go and you smack into the wall. your momentum is going to go from whatever it is here, p, to 0. Right? Once your velocity come to a complete stop, well, your mass times 0 is 0. So your momentum goes to 0. Therefore, your change in momentum, we can't do anything about. But what we want to do is to make this as small as possible to protect the occupant. Right? Now, since our net force times our time is going to equal whatever your change in momentum is for a collision, in order to reduce the amount of force acting upon the occupant, we're going to have to increase the time that that collision occurs. Now, that's pretty simple physics. However, the engineering, right, is a little bit more challenging. How do you increase the time that a collision occurs? Right? Well, one option is airbags. Right? Airbags will act on the occupant to sort of slow your rate of descent, or your reduce your acceleration that's acting on the occupant. And another is a crumple zone. So the front of a car is actually made to crumple, or made to crush. Now, the center of your car is made to be a strong cage. You don't want the center of the car crushing, because then the occupant gets crushed. But the front and rear of the car are made to crumple. And there's no occupants in there, so we can actually have them crumple. Right? And crumpling them takes time. Right? And that's going to help increase the time of the collision. This is great for a front or rear collision. Side collisions don't have a lot of crumple room there if you get hit in the side of your vehicle. So again, simple physics, just increase the time of the collision. Difficult engineering. How are you going to do that? Right? Obviously, seatbelts are important too. Always wear your seatbelts. Okay, now this equation works great if the net force acting on the object is constant, right? But what if it's not constant? What if net force is changing? Like, for example, a rocket. So we have a rocket, right? And let's say we have the force acting on the rocket and your time over here. The rocket will initially have a lot of force. It's initially just sitting there on the ground, not doing anything. So you need a lot of force to get it to go up. But as it goes up, right, it's using fuel and therefore expelling that fuel, and its mass is decreasing. So its acceleration is increasing as it goes up. So in order to reduce that acceleration, because you'll get a point where the astronauts are just going to black out. So in order to stop that from happening and reduce the acceleration, the engines have to actually reduce the force that is acting on the rocket. So how do you calculate the impulse of that? Well, in a case like this, you can find the area under your force-time graph. The area under your force-time graph will be your impulse. Okay? I think that's all I wanted to mention in this lesson. So let's try the questions on the back. Question number 1 I already talked about. Why is follow-through important? If you want to know that, rewind the video. Question number 2, we'll try. It's not too hard. It's fairly plug and play. Here we have, what velocity will a 41 kilogram child sitting on a 21 kilogram wagon acquire if pushed from rest with an average force of 75 newtons west for 2 seconds? Okay. So let's take our impulse equals change in momentum. So our net force times time equals mass times our change in velocity. All right. Now, it looks like everything's acting west. So let's just make west our positive direction. Yes, we did a lot of work with energies and we were free to no longer think about vectors anymore until now. So now we do need to think about vectors again. All right, so here we have our net force times time. And they tell us our net force, right? They say it's an average force 75 newtons west. And I think we can assume any other type of frictional force or anything like that. Okay, because wagon has wheels, and let's just say the coefficient of friction is so small we can ignore it. They give us mass. Well, the mass will be the sum of those two masses. They give us time, okay, and they give us initial velocity. This is very important. This is still change in velocity, not just v, delta v. And delta v is our final velocity minus our initial velocity. But in this case, they do tell us the initial velocity is 0 because it started from rest. So we're left with force times time is mass times final velocity. Okay, and since we're solving for final velocity, we can just rearrange this equation. Okay, and this will be total mass. Okay, so it's 41 kilograms plus 21 kilograms, and when we substitute that into our calculator and try it yourself, you get 2.4 meters per second west. Okay? And I'll see you tomorrow. Reminder, tomorrow we're doing the meeting with the physicist from IQC at Waterloo University at 2:20. Okay? Make sure you come to that. It's going to be great.